We will now discuss theorems 10.10 and 10.11. Theorem 10.10 states that if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is the right angle. In other words, if one looks at this diagram to the right of a circle, which you will see in a few seconds, angle B is a right angle if and only if line segment AC is a diameter of the circle. So let's take a closer look at what this theorem is saying and why this is true. So let's enlarge this picture a little bit so we can see the this right triangle. Okay, so we're first it is first stated that if ABC is a right triangle, then AC is the diameter of a circle. So let's assume that ABC is a right triangle, and assume that the right angle is at angle B. From what we learned recently about inscribed angles, we know that the measure of an inscribed angle is exactly 1/2 of the measure of the arc that it intercepts. So if ABC is a right triangle and B is the right angle, then that means that arc AC has to be equal to twice the measure of arc AC has to be equal to twice the measure of angle B. Well, angle B is a right angle, which is 90 degrees. That would mean that arc AC would have to be 2 times 90, or 180 degrees, which would make it a semicircle. And if AC were a semicircle, if arc AC were a semicircle, then line segment AC would necessarily have to be a diameter. So that proves that if a right triangle is inscribed in a circle, then its hypotenuse must be a diameter. Similarly, if we have a triangle inscribed in a circle such that one of its sides is a diameter, then it must be a right triangle. And the reason for that is one that you can see here. If we have a triangle where one of its sides is a diameter, it means, let's say in this case AC, it means that angle B must therefore intercept a semicircle, because that's what arc AC would be if line segment AC were a diameter. If angle B intercepts a semicircle, that would mean that angle B would have to be 1/2 of the measure of arc AC, which would be 180. 1/2 of 180 is 90, and therefore triangle ABC would be a right triangle where angle B is a 90-degree angle. So that proves theorem 10.10. Let's take a look now at theorem 10.11. Theorem 10.11 states that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. And in this case, we're given a diagram of a circle where we have points D, E, F, and G. C is the center of the circle. And we are told that if this quadrilateral could be inscribed in a circle, we must have that the measure of angle E plus the measure of angle G, which are opposite angles, must equal to 180, and that the measure of angle D plus the measure of angle F, again opposite angles of this quadrilateral, must also equal to 180. In this video, I'm going to prove the necessity, not necessarily the sufficiency. In other words, I'm going to prove that if you are given a quadrilateral that is inscribed in a circle, then you must have the opposite angles being supplementary. So let's take a look at this drawing here. This is a drawing of the same scenario, the same circle, where we have maybe a slightly different shape, but we nevertheless have D, E, F, G inscribed in the circle. It's a quadrilateral. And we're being asked to prove that, in this case, we're being asked to prove that angle E, for example, plus angle G, which are opposite angles, are equal to 180 degrees, and that angle F, or the measure of angle F, plus the measure of angle D must also equal to 180 degrees. Well, this isn't too hard to prove, so let's go about doing it. We do know that angle E is equal to half, being an inscribed angle, it's equal to half the measure of the arc that it intercepts. So that, let's start with angle E. Angle E is equal to 1/2 the measure. What angle does angle E intercept? FD, arc. It intercepts arc FD. 1/2, angle E would be 1/2 the measure of arc FD. Okay, and angle G from up here would equal to 1/2 the measure of the arc that it intercepts. Well, G intercepts arc FD as well, but this would be the minor arc FD, whereas angle E intercepted the major arc FD. In fact, it would probably be a little more accurate to say that angle E intercepted half of FGD, the big part of arc FD. So let's rewrite this as saying that angle E equals 1/2 the measure of FGD. Okay, so now we've got these two equations. We know that angle G is 1/2 of the measure of FD, and angle E is 1/2 of the measure of FGD going around this way. If we add both equations together, we end up by getting that angle G plus angle E equals 1/2 times the measure of arc FD plus the measure of arc FGD. But notice, the measure of FD plus the measure of FGD, FD plus FGD, is equal to a full circle. It's equal to 360 degrees. So this is another way of saying, and we can just move a little bit over here to finish the equation, that angle G plus angle E is equal to 1/2 times 360, or 180 degrees. Well, it so happens that that is what we needed to show up here, that angle G plus angle E is equal to 180 degrees. We can similarly show that angle F plus angle D added together, the measures added together, would equal to 180 degrees. So this proves that if we have a quadrilateral that is inscribed inside a circle, then by necessity opposite angles must be supplementary.